Hello, my name is Daniel Salibar. I am a second-year master's student from Purdue University. Thank you for listening to this presentation on deriving performance measures from vehicle trajectory data. We're going to start by talking about the message of the study. Traffic signal performance measures can help operators identify locations that have retiming needs. After these retimings are done, we can have improvements in delay and also in safety. Currently, these performance measures are calculated from high-resolution traffic signal controller event data, which provides information on an intersection-by-intersection basis and requires a significant capital investment. For these performance measures, we need the information from detector events and output events that are sent to a controller that's saving this information in data loggers. After this information is sent to a relational database from where we can then calculate performance measures. These are a couple of examples of equipment that's needed for this type of performance measures. In contrast, with the increasing popularity of connected and autonomous vehicles, billions of vehicle trajectory points are generated each month in the United States. With this high volume of data, we can state that our vehicles know more about our traffic signal systems than we know. This is why we're proposing to use high-fidelity vehicle trajectory data to calculate performance measures. The location of this study is an 8 intersection segment of State Route 37 that's located south of Indianapolis. To understand some of the performance measures that we're proposing, we need to understand what control delay is. Here we have a time-space diagram, and the first blue line is the location of a stop bar. The second blue line is the location of the far side of the intersection, and this black line is a free flow trajectory, which is a trajectory that's traveling through the intersection at the posted speed limit. So trajectories are traveling from top to bottom in this graphic. If we draw one of our trajectories, we can define control delay. So control delay is going to be the summation of the deceleration delay, the stop delay, and the acceleration delay. And we can see that the difference in this space between the free flow trajectory and the trajectory is going to give us the control delay. Now that we know what control delay is, we can learn what the level of service from the highway capacity manual is. The level of service gives a letter grade to different locations depending on the control delay. So locations with minimum delay are going to be given a letter A, whereas locations with significant delay of greater than 80 seconds are going to be given a letter F. So now we can start drawing our trajectories in this graphic, and we can start color coding them depending on the level of service that they have. So if we have a trajectory that has minimum delay, like the one we see on the screen right now, we can categorize this trajectory as having a level of service of A. Then we can keep doing this categorization with different other trajectories. And we can keep aggregating to fill the intersection for the time period that we're analyzing. At the end, we can have an overview of a specific traffic signal for the specific time of day. So in this scenario, we see that a significant amount of trajectories, 17% of them, have a level of service of E and F. Now, we're proposing a new graphic called the Purdue Prof diagram, which provides information on progression and split failures. Now we have the same graphic that we had before, but now we're color coding the trajectories based on the number of stops instead of the level of service that the trajectory is given. So if a trajectory does not stop when crossing through an intersection, we're going to be categorizing that trajectory as having arrived into the intersection during the green phase of the cycle. When we have trajectories that have a horizontal flat line, that means that that trajectory is a vehicle stopping. When we have vehicles that stop 2 times or more, that means that that trajectory had experienced split failures. This is important to know because that means that a complete cycle of the traffic signal was not enough for a vehicle to cross through the intersection. And again, we can aggregate more trajectories to have an overview of the intersection. So for this case, we have that 60% of the trajectories arrive on green, and a minimum amount of them had split failures. For the opposite direction, we see that the amount of split failures increased significantly, and we're going to see these results on the overview of the intersection. So here we see that 44% of the trajectories arrived during the green time of the cycle, whereas 12% of them had split failures. Now Hauli is going to talk to us about the proposed corridor-wide graphics. Hello everybody, I'm going to walk through the corridor-wide graphics in the next section here. So in this slide, we have on the upper left, the map of the 8 intersections that we're analyzing for this study. The data is for all the weekdays in July 2019, and it comprises of 115,000 trajectories, 1.4 million GPS points. On the right here, you see both for the northbound through movement and the southbound through movement, highlighted by the 2 red boxes here, the yellow gradation, which means that for split failures, we see about 25% of the trajectories experiencing at those times of day. So if you look at the left turn movements for both northbound and southbound, see a coloration is a little more intense, highlighted by this red box here. The reds and pinks signify that the split failure percentage is around 50% to above 50% for intersection 4 in this case, between the hours of about 4:45 p.m. to 6 p.m. There's areas where there's white that shows no data or very little data. These are T intersections or intersections that make left turns into rural or very low volume roads. Now let's look at the arrivals on green. The first red box here, as you can see, between the hours of 9 a.m. to 2 p.m. show that there are a high number of trajectories that experience arrivals on green at lower than 50%. This is seen in both the northbound and southbound directions. For intersections 4 and 5, you can see that some of the challenges with arrivals on green are at intersections 4 and 5 between the hours of about 3:45 p.m. to about 6 o'clock p.m. For the left turn movements, you see here there's a lot of red, but not to be alarmed because a lot of these left turn movements are protected only movements where on the coordinated phases aren't really timed for. So now I will talk about some of the costs that are incurred to generate some of these performance metrics in the cloud. So on the left-hand figure here, it costs about $1.25 to analyze the data within the state of Indiana for all weekdays in July 2019 on Google's BigQuery platform. The figure on the right is the corridor level view for 8 intersections for movement over 24-hour period. This figure costs $65.92. As we look to leveraging more cloud services to store some of this data, this demonstrates a unique opportunity to use some of these services for generating what traditionally have been on-premise type of solutions. And with that, I will conclude the presentation. Thank you for your attention, and any questions that you may have, please type in the chat box. Have a good day.